Hi class, so today I will teach you the short version of the chapter 4. Is it the properties of the pure substances? As you know, for the first 3 chapters, I taught the full lesson and uploaded it into the website. But as the university's request, we only need to upload the short version. That means each lesson, I only need to have the short version is about 10 to 15 minutes and upload it into the website. After that, for the full lesson, I will teach in the live stream version. So from this chapter on, I will only upload the short version. It's about only 10 or 15 minutes for each chapter. Okay, so now we go to chapter 4. That is the properties of the pure substances. In this chapter, we go through 5 parts. It's the pure substance and the phase change processes, the property diagrams, the property tables, the stable of the substances when phase changes, and equations of the state. Pure substances. So what is this pure substance? We regard this in the first lesson. Is it a basic concept? The pure substance is the substance that had a fixed chemical composition throughout. For example, in the air, we got the mixture of the nitrogen, oxygen, carbon dioxide, water, etc. So even the air, the mixture of several gases, but is considered to be the pure substance. So now we look at the phase change processes of a pure substance. Look at the example. We got a glass of water and we boiled it in the normal atmosphere. Here we got the 1 atmosphere as normal, at the normal. And as usual, when you put the thermometer in, you see the water will become hotter and hotter. And when, for example, it starts at 20 degrees, and when it goes up to the 100 degrees, it's starting boil. And when it's boiled, you still heat up the water, but the temperature doesn't increase. So in this case, where's the heat goes? The heat is not used to increase the temperature, but the heat in that case used to evaporate the water here. That means we call is the phase change. So we see that procedure. It means the thermometer here will be show at the 100. Sorry, it look ugly, but anyway, just believe that this one is the thermometer. Okay, so this one is the thermometer. To measure the temperature. Okay, so as starting, the temperature will increase from the 20 degrees up to the 100 degrees. Okay, so you see that the heat or the energy used to increase the temperature from 20 degrees to the 100 degrees based on the formula, you know, Q is equal to mc delta T. Delta T here is a T2 minus T1. This one is the initial temperature, and this one is the final temperature. So this Q is used to increase the temperature. So the Q here, they call is a sensible heat. The sensible heat. So you know the word sensible, right? Sensible or sensitive or sensor. It means something you can feel it. Okay? So for example, when the heat is supplied for the water, you can see the heat that exists by seeing the temperatures increase. So this one we call the sensible heat. But the Q, when it changes heat to change phase of water, that means it's from the liquid to the vapor, liquid to the vapor. So this heat, you cannot sense it, you cannot see it exist. For example, when the water is reached 100 degrees, you still supply the heat here, but the heat doesn't show by the increasing of the temperature, but it's used to change phases. So this heat we call the latent heat. Okay, so it's very important to distinguish between two kinds of heat. We call the sensible heat and latent heat. All right. So now, first, the water in the phase we call that being the compressed liquid or the subcooled liquid. That means the substance that is not about the vaporized. And next is we call the saturated liquid. That means a liquid that is about to vaporize. Okay, so the first stage is we call the stage 1 in the picture of your left hand side. That is at 1 atmosphere and the temperature 20 degrees. The water will exist in the liquid phase, that's mean the compressed liquid. When it go up to the 100 degrees with 1 atmosphere, that is the water exists at the liquid that is ready to vaporize. We call that is a saturated liquid. I mean stage 1, this one is stage 2. Next, when the water starting to evaporate, what they call is a saturated liquid vapor mixture. This stage at which the liquid and the vapor phases coexist in equilibrium. That means the stage 3 here, you can see is part of them is the saturated vapor and part of them is the saturated liquid. As more heat is transferred, part of the saturated liquid vaporize. So we got the saturated liquid vapor mixture. And then we go to the stage 4. That means when all the liquid is transferred into the vapor phase, that stage we call saturated vapor. A vapor that is about to condense. And stage 5, that means when is already all the water here, it become the vapor phase. We still continue to supply the heat here. In this case, we call it superheated vapor. That means a vapor that is not about to condense, not a saturated vapor. And then if you plot, so there is five stages as you show here. Remember, stage 1 we call the compressed liquid. Stage 2 is saturated liquid. Stage 3 is the saturated liquid vapor mixture. Stage 4 is saturated vapor, and stage 5 is superheated vapor. And we plot them in the TV diagram, for example, you see that is state 1, here is a compressed liquid, state 2 is saturated liquid, state 3 it's a saturated vapor and liquid mixture, state 4 it's the saturated vapor, and state 5 is the superheated vapor. You look at the picture here. And then that is this one we apply for the pressure of 1 atmosphere. Now we repeat the experiment with different pressure, and then we got the, for example, this line is for 0.01 megapascal. It is about 1 atmosphere, and then this one at the pressure of 0.1 megapascal, and this one is P as 1 megapascal, and this one is 8 megapascal, etc. So we repeat the experiments with different pressure and we plot them in the TV diagram. Okay, so property diagrams for the phase change processes we call the TV diagram. So as the supercritical pressure at this point we call this critical point. It means there's no distinction the phase change, boiling and the process. That means if we bring up to a certain pressure and the temperature of every substance, we will achieve the critical point. That means at above this critical point, the substance is not changed in 5 phases as we just mentioned, but it will jump directly from the liquid to the vapor. So the critical point, the point at which the saturated liquid and the saturated vapor state are identical. Okay, so the specific volume continually increase. No line to separate the compressed liquid and the superheated. And so above this critical point, we got the superheated vapor, and below this critical point, we got the compressed liquid. Okay, so and then we plot the line we can see at the picture on your left and your right hand side. This is the critical point, and we got 2 lines here. The line on your left hand side we call the saturated liquid line. That is it consists of all the saturated liquid state. We plot at the line on your left hand side. And in the right hand side we got the separated vapor lines. It is a combination of all the saturated vapor state, and it is a critical point. That means now the diagram will be separate into three zones. The first zone in your and left hand side we call the compressed liquid region or zone, and the region between the saturated liquid line and the saturated vapor line we call the saturated liquid vapor region, and in the right of the saturated vapor line we got at the superheated vapor region. Okay, so that means we you know that there are still 5 states can be presented in this diagram. So if the state belong to the compression region, liquid region, we got the first state, it is a compressed liquid state. If the state is stay on the saturated liquid line, we got the saturated liquid state. Okay, and if it in the saturated liquid vapor region, we got the saturated liquid vapor mixture state. And if it stayed in the saturated vapor line, we got that it is saturated vapor state. And last, if it stayed in this superheated vapor region, we got the superheated vapor state. Okay, so look at this example. In this one is the PV diagram. The previous one, it is the TV diagram. You see that the diagram also be divided in 3 regions. It is a compression liquid, it is a separated liquid, and it is when a superheated liquid. And if you include the solid in the diagram, you can see that this one is a solid, this one is solid and liquid, and this one is liquid. This one is liquid and vapor, and this one is the vapor. And this point we call is a triple line. That means this is a separate into the solid, liquid, and the vapor. So we call it a triple line. For example, for the water, as the temperature of 0.01 degrees Celsius and the pressure of 0.6117 kilopascal, we got is it a triple line, triple point, okay? And this one is a triple point. You see that means it separates the diagram in a 3 zone. In the solid phase, this one is liquid phase, and this one is the vapor phase. And we got the procedure as when the solid change to the liquid, we call that procedure as melting. Okay, so when the liquid become the vapor, we call is the vaporization. Okay, so when the solid become the vapor directly without changing in the liquid phase, we call it sublimation procedure or the sublimation process. Okay, so the sublimation means passing from the solid phase directly into the vapor phase. It's not changed to the liquid phase. So we call that is the sublimation. And the triple point here, that means for every substance we got the triple point. Okay, next is a property table. For most substances, relations among thermodynamics properties are too complex to be expressed by the simple equation. Therefore, properties are frequently presented in the form of the table. Some thermodynamics properties can be measured easily, but others cannot and are calculated by using the relation between them and measurable properties. The result of these measurements and calculation are presented in table in a convenient format is appendix. I already uploaded into your BKE learning. So for the enthalpy, it is a combination property. It H equals U plus PV, you know, huh? That is for 1 kilogram of for the unit of mass of the materials. We call the specific enthalpy. And for the m kilogram of the materials, we got the H capital equal to U capital plus PV. All right. So this is some unit that you can use or remember. The kilopascal time with the cubic meter, we got a kilojoule. The kilopascal time with the cubic meter per kilogram, we got kilojoule per kilogram. Bar time cubic meter, we got the 100 kilojoule. Megapascal time with cubic meter, we got 1000 kilojoule. And PSI is the power per square inch time with cubic foot equal to 0.18505 BTU. It means British thermal unit. So we got the table here. First we call the saturated liquid and the saturated vapor state. The table A4, it is the saturated properties of the liquid under the temperature. And the table A5, it is the saturation properties of the water under the pressure. For example, partial list of the table A4. I mean, we got the temperature, we will find out the pressure, and then we got the specific volume, we got the saturated liquid VF, it means the and saturated vapor is VG. Okay? And this one is the specific temperature. This one corresponding to saturation pressure. This one specific volume of saturated liquid, and this one is specific volume of the saturated vapor. And VF is specific volume of saturated liquid. VG is the specific volume of the saturated vapor. And VFG is difference between the VG and the VF. That is, the VFG equal to VG minus VF. And volume equal to specific volume times with mass. The enthalpy of the evaporation, we call the latent heat of evaporation, as I just showed you in this one we call the latent heat. So the latent heat of the evaporation, this one is the amount of the energy needed to vaporize a unit mass of the saturated liquid at the given temperature or the pressure. The saturated liquid and vapor mixture, quantity X is the ratio of the mass of the vapor to the total mass of the mixture. So the quality is between 0 to 1. So 0, that means it is the saturated liquid, and 1 is the saturated vapor. Look at the diagram, the PV diagram or the TV diagram. We got the saturated liquid state. That means if the substance stay in this line, its quality will be X equals 0. And if stayed in the right hand side line, that means the saturated vapor state, we got this one is the X equal to 1. So between the left line and the right line, we got that one is a mixture of the saturated liquid and saturated vapor. So X of that stage will be calculated by the M vapor divided by M total, with M total equal to M liquid plus M vapor equal to MF plus mg. So the temperature and pressure are dependent properties for the mixture. So the superheated vapor in the region to the right of the saturated vapor line and at the temperature above the critical point temperature, a substance exists as superheated vapor. In this region, temperature and the pressure are independent properties. For example, compare the saturated vapor, superheated vapor in characterized by lower pressure, higher temperature, higher specific volume, higher internal energies, and high enthalpy. So look at this one is a table. You can see that at one temperature we got in the different pressure, and its pressure we got the property like the specific volume here, the specific internal energy, and specific enthalpy. Okay, so we got this one is the a partial list of the table A6. So for the compressed liquid, a compressed liquid may be approximately as the saturated liquid at a given temperature. The compressed liquid properties depend on the temperature much more strongly than they do on pressure. Okay, so we got here a more accurate relation of a H. H will be nearly equal to HF at the temperature T plus VF at temperature T, P minus P saturated at the T temperature. Okay? Okay, so that is the end of the chapter of the property of the pure substance. So this one is a very, very short introduction. So hopefully when you go into the full lesson, you will understand more. But to be understand clearly, you must read the chapter that I provided to you in the BK e-learning in order to help you to understand more clearly. Okay, goodbye class.